bit of a change to the schedule. The first talk will be by Elchanan on generative networks and generative modeling, and then Kamalika will give the final talk.
Hey, good morning, everyone. Thank you, the organizers, for inviting me to speak. So I'm going to talk about something that I wanted to be presented more in this program in general, and we couldn't get some of the key people who work in this area to come, neither to this workshop, neither to the bootcamp or to the program in general. So I'm going to talk about a different perspective that some people are following. And I was trying to think about the way to do it when I don't talk just about my stuff, but I guess eventually I'm just going to talk about my stuff quite a bit of the time. So please, especially slow me down when I talk about other people's stuff. So. And feel free to stop me at any time. Okay, so the question that many of us ask ourselves is, why do deep networks work so well? And two of the kind of answers that we had is one, that they have a lot of expressive power, possibly. The other one is that they generalize well. And I think after sitting in the bootcamp, we are both a little unhappy. We are all a little unhappy with these answers. I mean, I think that Peter and Sasha were not trying to oversell the power of the VC or the statistical learning theory perspective. And it was sort of clear that we don't understand too much about how does this apply in the deep network setup. And also, Matus in his lecture said, I have this lower bound, but this lower bound, shouldn't have this crazy Lipschitz function. So, maybe that's not what we really see in real data. So the perspective I'm trying to think about for a few years, and many people have started thinking about it even well before me, and maybe have a better explanation, is it's about the data. And somehow the claim is that they work well for data that is generated in somehow a deep way on its own, right? So the data is generated in some hierarchical fashion, and this hierarchical fashion is the reason that deep nets work well. Okay, so that's the perspective that I'm going to take in this talk. We're good? Okay, so let's try to think, what does it mean? So what is our goal? So let me just maybe take a step back. I think most of the talks in this workshop or in this bootcamp are saying, okay, people in practice these days apply deep net and do some version of gradient descent, and they get great results. Let's try to understand why this happened, or maybe let's try to tweak the parameters a little bit to do a little better. My perspective is different. I'm not trying to say, even though this is one of the goals of the program, I'm not trying to say, I'm going to come up with a great theory of super gradient descent, which I'm going to sell to the Google people. It will make me a millionaire, and things will be classified 0.01% better. That's not my goal here. My goal is to take a step back and try to understand, in the big picture somehow, why do we need something like deep nets to work? Okay, so that's the goal. We want to understand data models that seem reasonable, that explain why deep nets work. Okay, so what do we mean by that? So it's not really clear, but I'll tell you the perspectives I chose for this talk. And maybe before the perspective, let me tell you why would this make us happy. So first of all, we had many talks where it was clear that we really want to understand why and when deep networks works and why not, in particular in contexts such as adversarial settings. It would be good if we can get provable algorithms for inference. So what is provable algorithms? Provable algorithms, anybody who's done statistics, I'm not going to prove to you that your car is going to drive and not crash. What I'm going to prove to you is that if the data is generated according to a model that I specify, my algorithm does what it's supposed to be doing, right? So that's what I mean by provable algorithm. Maybe even if we are very lucky and very smart, we can get robust provable algorithms, which says, it's not only if you're generated according to the data, that the model of data that you came up with, even if there's some small tweak or differences, your algorithm is still going to work well. And finally, somehow from a theory perspective, it's very interesting to understand, why do you need depth? Why is depth needed? Why can't we just use models with 2 layers? Or why can't we just use kernels or something to do whatever we're doing? So that's the dream. We're not going to satisfy this dream today, but when I have a dream, this is my dream, right? Some people have different dreams, this is my dream. Okay, well, let's do that, that would be amazing. We're good? Okay, so that's what I want. Okay, so I'm going to criticize everybody in the community, including myself. I'm going to criticize people in 2 ways. First of all, I'm going to not talk about many works that are relevant to this, just because there's no time and I don't know all of the works and so on and so forth. So everybody I offend by not mentioning, please don't be offended. And the second, everybody I'm going to mention, I'm going to offend. I'm going to say, why some of the criteria are not satisfied. So, just be prepared that I'm going to offend everybody. So these are the criteria that I'm going to consider. And as you see, there's going to be some tension between them. So first criteria is somehow in the very applied side, we want a realistic model of the data, right? So I don't want a model of the data which says, well, the data is generated on an algebraic variety with some curvature, and I'm a mathematician, I like stuff like that, but this is not our data, right? So we want somewhat realistic models. The second criteria that I want provable algorithms that can actually recover the inference procedure, right? So I don't just want to say there's a local minimum, blah, blah, blah. I want to say that if this is your data, here's a provable algorithm that runs in so much time and so much data that does give you a classifier. I don't think we've seen any talk like that in this workshop. Right? So I want something much stronger than what we're used to. And the third thing, which we saw a little bit just in Mathu's talk, is depth. I want to prove that depth is needed. I can come up with an algorithm that's very sophisticated, but in fact, if you do linear classification, you're done. So obviously, there's tension between these three objectives, right? There's realism. The more realistic stuff is, the harder it is to model, the harder it is to analyze, right? So if it's very realistic, I'm not going to be able to do task 2 and 3. If I can reconstruct, if I have very efficient algorithms for reconstruction, even if the model is not completely realistic, you might think that it's actually hard to be able to prove lower bounds on depth. Right? Because I have an algorithm, right? So if I have an algorithm, then maybe the depth doesn't buy me too much, right? So these three objectives are somewhat in tension, and for the last few years, me and a few other people who are not represented again in this community are thinking about this problem, maybe from this perspective, some from other perspectives too, and trying to understand can we answer all of these questions simultaneously. We're good? Okay, so that's what we want to do. Okay, so what I'm going to do, like I said, what I'm going to do is, first of all, I'm going to offend everybody in the next 10 or 15 minutes, and I'm going to come up with my own model, which is not perfect either, and, and I'm going to offend myself. And then, feel free to participate at any point. Okay, so since we are the Simons Institute for Theory of Computing, if you are somebody who just did theory all your life, and somebody tells you there are these deep nets and nobody understands why do we need depths, you raise your hand and you said, we have circuit lower bounds. I understand why do we need depths. How many of you have seen circuit lower bounds? Okay, so many of you have seen circuit lower bounds. So I said, okay, what is the circuit lower bounds? So let's just make a caricature of what does it mean in our setting. So in our setting, circuit lower bounds will be the following. Well, what is the data? The data is what you like. It's xi, which is high dimensional, and yi. What is the xi? The xi is just uniform on the discrete cube. What is the y? The y is f of xi. And what is the f? F is a polynomial size circuit of depth d. Okay, and what is a circuit? In the classical computational complexity, you have n unbounded fund n and OR gates, and you have NOT gates. Okay, so that's the model that we're looking at. What do we know? So there's a long line of work. I'm just going to summarize it in one slide, maybe in the strongest results. So this is a result by Rossmann, Servideo, and Tan, and slightly strengthened by Hastad, who actually proved the original result, not in the probabilistic setup, but here's what they do. So there's a long line of work here, which I'm summarizing, but the best result in this area. So if you have a circuit of size order n, of depth d, okay, so this is what we want. And what do we know? What's the depth separation that we get? We get that any circuits G of depth 1 less, d minus 1, that classifies slightly better than random. So the probability that g of x is not equal to f of x, which is the correct label, is less than half minus epsilon, must be of size exponential in n to the 1 over d. So there are circuits of depth d minus 1. There are circuits of set d. I give you a specific function of depth d. This is going to be my labeling of the data. X is at random. You understand the distribution. Y is just f of x. F is a very explicit function. And you want to do it with depth d minus 1. If you want to do it with depth d minus 1 and you just want to label to classify better than random, then you need this very big size. You good? This is very strong separation result. So let's ask about the score. And I decided, so you'll help me offend everybody. So how realistic is this model for data? Anybody wants to give me a number? No data looks like that. So for me, this is 0. Okay? Is there a reconstruction algorithm for the circuits?
What's the scale of the grades?
0 to 10. Thank you. Yeah, 0 to 10. Thank you for asking. This is a very good question. So 0, you see you have an applied person here. He wants to knows to the scale. So it's 0 to 10, and so it's clear that it's not very realistic. These people didn't think about inference at all. They didn't think about how to reconstruct the circuit. So I'm also going to give them 0 about reconstruction. This is an explicit reconstruction of one circuit. But the depth is the best that you can get. So for me, again, they didn't think about the 3 perspective that I presented at the beginning of the talk. But the depth they nailed down. They get 10. Right? There's no question about it. You cannot do anything better. It's explicit. It's under distribution. They didn't think about reconstruction at all. That wasn't their objective. In general, we know that reconstructing circuits is very hard, and it's not very realistic, so they get 10, 0, 0. Yes, please.
Yeah, so I agree it's not a very realistic model of data, but maybe it's a good model of data with some of the labels randomized.
Yeah, I'm not sure. So there is even an easier model where you just label some of the labels are really at random. And for this model, much more is known. For this model, it's much easier to show that you need a big circuit in order to agree with the data. Right? So these are somehow stronger. I agree. So maybe you're right in the sense that even before this model, I could have come up with an even simpler model, where the x is IID chosen from the cube, and the y is completely independent and random, and then I try to fit a circuit or any function to fit this data, and then the classical theory of VC dimension or whatever will tell me that I will need a very big object in order to do that. Right? So that's fair. This is a little different, right? Because what you say, okay, there is a the y is generated in a principled way from the x's. That's a good comment. So. Good. Other questions, comments? Okay. So I promised to offend everybody, so let's offend Matus. So here is a slide for Matus talk. This is the function that he constructed. So this function that goes up and down many, many times. And you were all here. So of course, Matus doesn't think that real data looks like that. But the model, if you want, is the following model. The x's are chosen uniformly in the interval 0, 1. yi is going to be f of xi. And what is f? F is this explicit, or it's the function that we've seen over there that goes up and down exponentially many times. It's explicit order d square size depth ReLU network, such that any ReLU network of depth d that agree with f a lot, maybe the probability that the expected value of the difference, Matus can get something much better, but let's say just 1 over 100, has to be of size exponential in d. Okay, so that's we've all seen. The construction is very nice. We all enjoyed the proof. It was great. Okay, let's still score Matus on these objectives. Okay, so maybe because he's here, let me do it. I'll do it. I won't ask you to offend him. So I think in depth, I would give him a 9. I won't give him a 10, sorry, because there isn't a separation between, this is fantastic, but there isn't a separation between d and d plus 1, which is something that in principle we would like, right? So there's just a separation, between d and d squared. So we lose something there. Reconstruction, I still give him 0. He didn't really think about reconstruction. That wasn't the objective. And realism is 2 because at least it's real valued. It looks more like data model that we will consider. Are you going to appeal the score? Objection?
I would actually reduce it.
Yeah?
Could we even hope for such a separation between d and d plus 1 for univariate functions?
Probably not, but still, we haven't restricted Matus or anybody else to just consider univariate functions, right?
Yeah,
so that's
for univariate, I think it's actually probably false, but no one cares that univariate.
Yeah. So that's a good. But I would just giving it as an example. If you came up with an example that's multivariate and real valued, where you have a good separation between d and d plus 1, you will get a score 10 here. I will still give you 0 here and 2 here or something, but you will get a 10 there. Okay. Very good. Okay, good. So that's another approach. Okay, the proof is elegant. We all enjoyed it. Okay, let's do candidate 2. Candidate 2 is hacker model. So if you live in the world of deep nets, everything is deep nets. So you say, the data is also generated by deep nets. We all know that that's the case. Everything in life is deep nets, either for inference or for generation. So what are we going to do? We are going to use some model that's reversible, where you generate the data going down, you're going to do the inference going up, maybe you're going to do GANs, you have a couple of networks talking to each other, one is going to generate the data, one is going to discriminate, you're going to do variational autoencoders, there's all these techniques that just say the data is also a network. Okay, I don't know this technique so well, so I let you suggest scores. So actually the hardest score for me is realism. So how realistic is the data that is generated by this nets? It's pretty good, right? So it's 8, 9, 10?
In some data sets, it does seem to memorize little patches. So
Okay, so here's what I gave it. I gave it on realism, I gave it 9. I mean, from what I'm seeing at glance, the distribution is not exactly the same. You see something that looks okay, but if you look at the details or something, sometimes you miss, sometimes it doesn't really look like you want. Reconstruction, there are algorithms, but we have no proof, right? So there are algorithms to do all of these procedures. That's why people are using them, but we have no proof that they do what they're supposed to do, so let me just give it 2. And similarly for depths, it feels like you need depths, but we have no proof that you need depths in this setup. We're good? Okay. But smart people have thought about this before, and they said, okay, maybe we can prove something in this setup. So this is a very nice paper by Sanjeev Arora from about 5 or 6 years ago, and a bunch of his collaborators, which unfortunately I didn't write down. And they looked at random sparse generative models. So, and maybe I'll draw something on the board, because I didn't steal any picture from the paper or from the slide. So what does it mean? So you have a network where the basic assumption is that it's very sparse, so the average degree is very low, especially, and in their construction, the average degree goes up as you go down the levels. And the assumption also, when you go in this direction, you start with a vector that's mostly 0. So maybe there's a little bit of 1s here. So when you go in this direction, the generation process, you will have very few 1s here, and so on and so forth. So that's the model that they constructed. And it's random also. So all of these connections are random edges. Okay, so that's the model that they had. And what do they prove for that? So they prove two very nice properties. The first theorem that they prove is that going up and going down with high probability, you get what is called autoencoder. What does it mean, autoencoder? It means that if you go in this direction and then you apply rel, you essentially just shifted going back in the other direction, you get the identity function with high probability. Okay, so maybe f down at level D composed with f up at levels, maybe I. F up at level, okay, we have to enumerate it somehow, I plus 1. The probability over in their setup that f down, f up, x equal the identity of x is high. It's almost. And that's what they proved in their model, which is very nice. And they also found an efficient algorithm for learning the network. So if the data is generated according to this network, they have an algorithm that recovers the network. So good. How many of you have not seen this work? Oh, wow, I should have really spent more time on this. So let me try to spend more time on it. This is really very nice work. And the score I gave it, okay, you didn't see it, so I can give it any score I want. And Sanjeev is also not here, so it's easy. Okay? So I'm sure he's watching live. He has nothing better to do with his life. So, the score I gave it, so reconstruction, it gets 9, and it gets 9 because it reconstructs. I mean, it's not robust reconstruction, so maybe giving a 10 is a bit too much. So it's really doing this job. Realism is a bit tricky. I mean, I think the sparsity is maybe okay, but assuming that the connections are random is a bit tricky. I don't think people some people are nodding their head about this random connection. I think they are aware of that too. And I think that's the reason maybe they didn't pursue this line of work too much. So I'll give it a 5. It does look a little bit like a network, so I'll give it a 5. In terms of depth, I don't give it a 0 or 1 or a 2 because they definitely thought about it. You know, if you read a paper, they say, we believe that there is a depth separation here, but they don't actually prove it. They claim that they prove something about 1 and 2 layers, but if you read what they actually prove, it's some average case sense, which doesn't really prove much. So they at least were thinking about depth, so we'll give them points for that. I think they know that it's not really realistic, but it's somewhat realistic, right? It does have the structure that we want. It is a reversible network where you can prove it's reversible, and so this is a very good attempt. And there might be something in this direction that one can think about, in particular, if you somehow are successful in making the randomness assumption a little weaker. Anybody wants to see some ideas from the proof here? Nobody? Oh, wow. I'll tell you a little bit. It's depressing. Okay, so what's nice about this sparse random situation is that things are very easy. In particular, a key property that I have is what's called unique neighbor. Some version of a unique neighbor. Which means the following. Suppose you look at the level, but the last one. So the level but the last one, by the construction, most of the vectors are 0, and maybe you have some 1 and minus 1s here. Okay. Now, you look at any guy down here. So again, most of the guys here at the last layer even are going to be 0. But you look at the guy that's not 0. So maybe this is not 0. So let me just write not 0. In principle, it can take many values, but suppose that this is not 0. The unique neighbor property says that it's not 0 just because of one guy. Because it's a random sparse network, it may be connected to this guy, but the probability that it's connected both to this non-zero guy and to this non-zero guy is small, so this will never happen. Okay, so most of the time when you're not 0, it's because of one guy on top of you. Okay, so why is this nice to have this unique neighbor property? So one reason that it's nice, you can look at all the neighbors of this guy, and what will happen with all the neighbors of this guy? So it's sparse, so there aren't too many neighbors of this guy. And what will happen with them is that they're either equal to this guy or to minus this guy. In the network, you essentially only have plus one and minus one weights. So you have all of these guys that agree with these guys, except maybe for a sign flip. So if you want to know this guy, you can just look at the majority of these guys with the corresponding signs, and you're going to get this guy, and even with a little bit of error correction. Because they have multiple copies with different signs. So if you know the structure of the network, you can do this auto-encoding property, right? You can go up this way. Looking at all the neighbors of this guy, all the neighbors of this guy are going to be non-zero. You know which one are going to have the same sign and which one are going to be the opposite sign. It's very easy to reconstruct given this information. Even one is enough, but if you have multiple, you can even do a little bit of error correcting. Okay, so this gives you the auto-encoding property.
So, Elchanan,
yeah.
We should think the depth is fixed and the dimension is very large. Like
I think that's in their model. I think that's essentially what they do because the sparsity goes like powers of n, right? So maybe the depth is 100, but it's very very wide. Yeah, thanks. Okay, so that's one. Thank you, Seb. So that's one nice property. That's the auto-encoding, and the other property that's nice is what's called the Hebbian principle, which in this case is super nice. Is that things that fire together are wired together. Suppose now I don't know the structure of the network and I want to recover the structure of the network. How will I recover the structure of the network? So again, here I have the last layer. I want to recover the structure of the network. So here's a very naive algorithm. I'm going to sort of classify guys. I'm going to say, if these two guys are non-zero, a lot of the time, I'm going to say that they have the same parent. Okay, so the rule for deciding for two vertices to have the same parents is that if they are non-zero often. If they are non-zero often, I'm going to say that they have the same parent. And because of the sparsity and the fact that usually they're non-zero, usually they have only one parent that's non-zero, this will be a very good reconstruction procedure for the guy in the previous level. Okay, and then you do it recursively somehow. You have to control the dependencies. There's some technical depth in this result, but that's the basic intuition behind this. Very good? Questions? Okay, good. Okay, so now comes something that it's very hard for me to talk about for various reasons. First of all, it's very difficult. Second thing, I don't understand it. And the third thing is beautiful. Okay, so we can run a full program on the scattering transform. How many of you are comfortable with wavelet? I know at least one person in the room. Okay, so some of you are comfortable with wavelets. So Malat and later in joint work with Juan Bruna came up with a data generative model, which is a very natural model for two-dimensional images. And I'll try to explain you a little bit of what it is, but I mean, I'm not really an expert in this, and I'll just try to give you a very brief outline of the main feature of this model. So what they were looking for is they were looking for a model of images that it's continuous with respect to deformation at different scales. So we all know that images, right? So images are sort of, what do we expect from images? We expect that an image and a rotation of the image will have the same meaning. Okay, so this is a simple deformation. But you also expect that, if you don't just rotate, you do some continuous thing, maybe you take my picture and you make this leg a little fatter than another leg. You would still recognize it's me. Maybe my legs are not even symmetric right now, right? So there's some deformation here that you do that's not really an algebraic, it doesn't have an algebraic, it's not an isometry, right? You change this a little bit more, maybe my head is becoming even bigger, this ears are, at some point it's going to become ridiculous, but as long as these deformations are small, you say, okay, this is still Elchanan, okay? So that was the objective, and they came up with a model that does that. And somehow what's nice for this generative process that they came up with is that, in the generative model, somehow energy moves from high frequencies to low frequencies, right? So it's so maybe I'll try to draw, I stole some, so I talk a lot about, or talk some about this with Juan Bruna, so everything I say that's true is because of him, everything I say is wrong is because I didn't understand what he told me. But somehow, the picture that they have in mind is a picture that at the high level, so you have something complex, so you have a lot of high frequencies. And then you go down, you sort of localize it. So this is some intermediate level. So here you have some intermediate frequencies. And eventually when you go down, you get these small little patches. And in these small little patches, you only have low frequencies. I don't know if it helps or not, but that's somehow the intuition of what they're doing. So I'll show you some slides that I stole from Juan. And so the basic idea is that you convolve at different layers with different convolutions. So you start from a high-level concept, and you convolve. Then you do this local convolution. Then you do more localized convolution. Then you do more localized convolution. And to keep this continuity, it's nice that all of these convolutions are contractive, so they don't raise the norm, right? So that's somehow a key property of this process. And okay, so there's these beautiful pictures which I won't try to really understand because I explain because I didn't have enough time to go in details. But somehow what's nice about this process, and maybe is when you go back, there's something that's very nice. So you somehow do something nonlinear to get from these low frequencies these high frequencies, right? So you do some operation like the one that we do in deep nets. So there's some nonlinear filters when you go from the bottom to the top that recover the high frequencies, right? So if you can think about high frequencies, this is something very, very detailed and delicate. And low frequencies like pixels, and somehow you go up, you get this higher and higher frequencies, you get information that's richer and richer, and you do it via this nonlinear filtering procedure. Okay. I expect that nobody understands what I said because this is very hard, and I don't really understand it. And I was actually talking to Juan before preparing this talk, and the question is, to what extent can they prove that you actually need depth in order to do inference in these models? And it's not completely clear. We are still trying to understand what it is. I think this might be a good idea for somebody who wants to do something on the interface between theory and signal processing. There's something that one can try to prove here more formally than they did. But the score I would give it, okay, is realism is 8. They then generate very nice pictures. I mean, I don't think they really compete with what deep nets do, but they generate very nice pictures. Reconstruction is a little tricky because somehow this model has a fixed architecture. So they don't, there isn't really, you cannot really tune parameters too much. You cannot really learn the non-linearities. It's just fixed non-linearities that you're using in it. It's just one model. And some people have been looking at it, but again, not from the theory perspective. There's a paper of Cohen and Max Welling from Microsoft. They show that they gave some sort of applied heuristic algorithm to learn these filters in a better way than just fixed filters. So I'd give it a 5. And again, the depth issue definitely Mala and Bruna thought about, and they make this claim that you need to go many layers in order to reconstruct because that's the only way to reveal the higher moments. But I think right now it's not at the level of theory. So if you want to prove some theory statement, I think, and you understand wavelength, I think that's a good place to go. So this is really beautiful. I mean, I think if anybody wants to talk to me about, connecting this to the kind of theory of computing during the program, I'm happy to do that. I mean, I think or just do it without me because I don't really understand wavelengths very well. I think there's something there to do that's interesting. Questions? Okay, good. Okay, so from now on, I'm going to tell you about my own stuff, which you should lower all the grades. I'm going to give myself 11, 11, 11 in everything. So just. Okay, so the question remains somehow, and the question is the natural data generative process with provable algorithm for learning the classifiers, and where the classifier provably requires depth. Okay, so that's the question that I want to ask right now, and the answer is going to be sort of yes. And some people have seen some version of this before, but when I prepared this talk, I realized there's a nice way to explain it. So I think this is the first time I explain it in this way. Okay, so here's the process that I like a lot. All of the people who know me immediately fall asleep. And I'll explain why this process, somehow gives us all of these things. Okay, so we're going to consider a process on a tree. The process is going to be the following process. The root is going to be colored randomly. And I'm going to go in an hierarchical fashion. Remember, this is what we want. We're going to copy the color with the parent independently for each edge with probability eta. And otherwise, we're going to choose a color that's independently uniform at random from 1 to q. So here there are just two colors. Maybe theta is pretty large. So at the first layer, I copied everybody. At the second layer, sometime I copy, sometimes I didn't copy. At the third layer, somehow I copy and didn't copy. And for the talk, and I think in all the papers, the few papers that this has been investigated, we will only consider full binary trees. You can consider more general trees. We'll only consider full binary trees to make our life easier. And more generally, and this will come up in some of the results that I'm going to mention later, I mean, this process doesn't have to be either copy or random. You can have any Markov chain on these edges here. So there's a Markov chain that decides what's the width from here to here. And it turns out that an important parameter that happens to be theta in this case is the second eigenvalue of the transition matrix. This is going to be the parameterization when we're going to talk about other processes. We're good? Okay, so that's the process that I'm going to talk about. Okay, so now I'm going to think about all of these criteria, and one of the reasons I want to give this talk is I'm somewhat excited about the fact that finally we can say something about depths on this, and everything other than depths we knew for a long time. So there's a lot of things that we knew for a long time. The depths is newer, so I think that somehow tells us a nice story about this model. Okay, so is this a good model for speech or images? It's a terrible model for speech and images. People have used Ising model for images, but not this simple Ising model. It will give you some fractal picture that you are not going to like. However, I think when you look at models that go in this recursive way, going from top to bottom, it gives you a nice abstraction of a multi-layer generative process that goes from the top to the bottom, right? So, that's a nice feature of this process. And what's the other nice thing about it is this, in fact, is a process that was invented in terms of data, or was considered in terms of data. It's a standard model of evolutionary dynamics of species. So since the 1970s, biologists have considered this model as the model of mutation among species. So Cavender, Ferris, Neyman, these are three different people. Neyman is Jerzy Neyman from Berkeley, who came up with this model as a model of genetic mutation among species. So it is a model of data. And it is also a standard model in statistical physics. It's called the Ising model, or the Potts model on the beta lattice. So it's studied since the 1920s in physics. So I don't know, is this a natural process or not? Like I said, I'm going to give myself an 11, so I gave myself a 6. Okay, it's not a model of images. It maybe has some features of model of images, this multi-layer thing. It's not a model of speech, but maybe it has some feature of that. And it is a model of some other kind of data, so I'm going to boost my score and give myself a 6. We're good? Okay, any objections? What is the best classifier? Okay, so now we are trying to understand this model in terms of all the questions that we ask. So what is the best classifier? So that's also nice. If you know the model, the best classifier is known, and the best classifier is just computing the posterior, and you are going to apply Bayes rule or unbelief propagation. You're going to run in linear time. If you know the structure of this net, then you're going to find the posterior, and you can classify very well. Question about that? Okay. What about learning? Yeah.
Aren't there some ways to beef up the generative process to make it still have the same hierarchical fractal structure, but is now a good model for images?
So I'll talk about that. So Matus is predicting what I'm going to talk about in half an hour. So I think some of them, even though many of you are sort of really want models of data, I want you to be patient for another half an hour, and then I'll try to talk about, once we took the insight from what this process is saying, what can we say about real models of data? So I'm going to talk about that. Yes, Peter?
What's the classifier? What does it mean to learn?
Oh, what's the class? Okay, sorry. So let me repeat again. What's the data and what's the? Okay, so the assumption is the following. So my y is going to be the root of the tree. Then I'm going to do this process over and over again. And what you're getting is the x.
So
So you want to classify y from the x, right? So somehow, and again, if you think about it in terms of the processes that we've seen, y is some high-level concept. I mean, you don't really refine it. We don't do this kind of things that Malad does, that of losing high frequencies. It's all of the same complexity, but we do localize it, right? So we move it left and right, left and right, left and right, duplicate with some noise, and then we have the x, and we want to infer the y. Thank you. So the best classifier of y given x is just doing belief propagation. It runs in linear time. It's optimal. We know everything about it. We're good? Okay, very boring. What about, so this is all old. What about provable algorithms for learning the classifier? So this is also something that's known for many years. These problems in biology of building these trees given samples, so maybe I'll say more about it later. Problem of given samples of x, even without the y. Learn the structure. This problem is a big area in computational biology. It's called phylogenetics. So people have done this in an applied way for many years, but we also have theory. There's a famous paper of Erdos, Steele, Sekeli, and Warno. I think Warno is here or going to be here in the next week or something. You can talk to her. So they have a polynomial time algorithm for learning the graphical model. Then, there are more refined work that I started about phase transition from sample complexity between logarithmic and polynomial, work about pack learning. We know how to learn this model. So in terms of the reconstruction score, I give it a 9. And again, the reason I give it a 9 and I don't give it a 10 is these algorithms are somewhat robust, but they're not completely robust. You want some more robustness, so I'll give it a 9. Okay, so I told you some old news. This process goes back to the 1920s. These algorithms go back like 10 or 15 years ago. What aspect I didn't tell you? The aspect I didn't tell you is about depth. So now I'm going to tell you about the depths. Is it really, do you really need depth? So the question that we ask ourselves, do you really need the depth in order to infer y from x? You good? Because that's the question. Okay, so let's think a little bit about what can we expect from the lower bound here. So the size of the object x, okay, so x is in the size of x, the dimension of x, which we are going to call n, is in our case going to be 2 to the d. Okay, because it is what it is. So we cannot really expect to get any depth lower bound better than log n, better than d. Because this process is of depth d, we cannot really get better than d. So we ask ourselves, is this reasonable or not? Then I went to Google and asked Google if this is reasonable or not. I think it's maybe not reasonable. At 2014, it was reasonable. Because if you look at VGGNet, it had about 16 layers and 100 million parameters. It sounds like log is the right scaling, maybe, so maybe we're happy. But we all know that the newer nets are deeper. So even ResNet has already 152 layers and only 2 million parameters. So maybe log is not the right scale. But it is what it is. That's what we can prove for this model. One can think about other models where maybe you have more depth somehow. But we are not going to get anything better than log. And what I'm going to tell you is what we know about depth lower bound for this model. And this is a paper we just put on the archive last month with Ankur Moitra and Colin Sandon. You good? Okay, so again, one criteria was, what were the 3 criteria? Realism, it's somewhat realistic, maybe not for most of the data we're looking at these days. Reconstruction algorithm we already have, and now we're going to talk about the depths. I have until 10:50. Okay, so we have to decide how much we want to do circuit lower bounds and how much we want to do other stuff. Who likes circuit lower bounds? Who doesn't like circuit lower bounds? Everybody is so positive in California. Okay, so say again?
Here's an easy.
Okay, very good. Kamalika, thank you. Okay, so I'll tell you a little bit about what we know, and then maybe we'll ask you this question again if you want to see something about the proof. So we want to talk about lower bounds, so we have to talk about which classes of circuits we're talking about. So maybe the weakest class you can consider is AC0, which is a class of bounded depth circuits with N and O and not gates, and N and O are unbounded fine. Okay, so this is one class of circuits that you can consider. And one thing that you can prove for this class is AC0. If you look at any function in AC0, bounded depth with this kind of gate, as the tree becomes bigger and bigger, you cannot classify better than random. Okay, so this class is not strong enough to do classification better than random. Okay, so we should ask ourselves a question here. first question we should ask ourselves, is this trivial? And this could be trivial for various reasons. One reason it could be trivial because when the tree becomes deeper and deeper, this inference problem you can just not solve. Maybe y is independent of x, and you cannot infer y at all, and then it's trivial. Nobody can do that. Even BP cannot do that. Okay, so that's not the case. It's not trivial. It's known that BP classifies better than random in this whenever 2 theta squared is bigger than 1, and sometimes also in other cases. Okay, so it's not trivial. There is a range of the parameters where BP classifies better than random. It can, in fact, when theta approaches 1, the classification error goes to 0. So in this situation, BP does a good job, it does the optimal job. But if you look at any bounded depth circuit in AC0, then you cannot do better than random. And another reason that it might be not trivial, and it took us quite by surprise when Colin observed this, is the following. In fact, while it cannot classify the process of generating the leaf distribution, you can do in AC0. You can do it in depths 2 or 3. Okay? So the backward, you say, oh, AC0, it's such a weak class, it cannot do anything, da, da, da. It's not the case. AC0 cannot do anything when it comes to inference. When it comes to inference, when you go up, you cannot do anything better than random. When you go down, you can actually generate this distribution exactly. Yeah?
Sorry, so the hardness or easiness must depend on theta, right? If theta is very close to half, it must be pretty hard, and we can't do anything. Good. So the statement of the theorem that AC0 cannot classify better than random is always true. Okay? When theta is small, theta is the copying probability. Let's say theta is close to 0. I think that's what you meant. What happens is even BP cannot classify better than random. AC0 can never classify better than random, but sometimes even information theoretically you cannot classify better than random. But there is a range of the parameter that information theoretically you can classify better than random when theta is bigger than 1 over square root of 2, but where AC0 cannot do anything. In the other range of parameter where BP is trivial, AC0 is also trivial because it's information theoretically trivial. Okay, but the statement of the theorem is true. You don't have to add any qualification to the theorem.
What happened to your second largest eigenvalue?
So the second eigenvalue is theta. This is what's important here, right? So it's when theta is bigger than 1 over square root of 2, this is one of the cases where we know that BP does better than random. Thank you.
Can you say a couple of words about the proof of the
Yes, but let me tell you all of the statements what we know, and then I'll tell you a little bit about the proof. Of the second, okay, we will see. I'll tell you a little bit. Okay, so this is one class. Let me go to the next class. TC0. TC0 you guys should like more. TC0 is like AC0, but you are also allowed to use majority gates, or in general, threshold functions, right? You can add bits, this is like, you can do sort of binary ReLU related stuff. So if you want, it's bounded deep nets. And here the picture is more complex. So when Q is equal to 2, so for the specific case when this transition matrix over here is a 2 by 2 matrix, so when this is the matrix theta times I plus 1 minus theta, so this is the case Q equal to 2, plus 1 minus theta times 1 half, 1 half, 1 half, 1 half. So in this specific case, we know that if theta is large enough but still smaller than 1, then TC0 classifies as well as BP. So with a bounded number of layers, you can classify as well as BP in TC0, and we conjecture that this is true for all theta when Q is equal to 2. Okay? So this, if you want lower bound, this is a little disappointing because I wanted to prove lower bound, and now I'm telling you that in TC0, you can do it with constant number of layers, so maybe it's a little disappointing. So maybe we can classify optimally in TC0 always, and maybe bounded depth net suffice. And now I ask you to keep this bit of information in your head. Like any talk about circuit complexity, there's some complexity. I'm going to go to the next slide, and I'm going to introduce yet another class.
Elchanan, do you know that Q equals, what about higher Q? Q equals...
This is also in the next slide. So there's some delicate relationship between what happens between TC0 and NC1, which is the next class I'm going to talk about. And I'm going to try to explain the story, the more delicate story that happens over there. Yeah.
And for the proof, are you just implementing BP in TC0?
No, I can also tell you about, okay, so I have one request for the proof for AC0, one request for the proof for TC0, and then, Ravi?
Slightly confused. Theta is very small.
Yeah.
The majority should tell you the story, right?
So again, theta is the copying probability.
Yeah.
It's a copy. I'm sorry.
So theta, what we're interested in the regime where there's information is where theta is close to 1. Next. Other question? Excellent questions. Good. Okay. So let me try to be patient for another one, and let me talk about another class, and then I will clarify the connection with TC0. So NC1 is the final class, is the class of order log n depth circuits with n and OR gates of bounded fan2, and NOT gates. And somehow what underlies all the question that you asked before is what is known is it's known that TC0 is contained in NC1, but it's not known if they're equal or not. Okay, so when we ask about TC0 versus NC1, the problem is the computational complexity theory. You guys did not tell us that if they're different or equal, right? So you can blame the computational complexity people. I will pretend not to be one of them. Okay, and what do we know about the class NC1? We know that one can classify as well as BP in NC1 for any model on the edges, any theta, any Q, any model, NC1 is enough for you. If you want to implement BP, you can do it in NC1. You don't need more than NC1. Okay, so NC1 is, definitely you are not going to go higher than NC1. And we also know that there is a broadcast process on the tree, which I won't define because it's complicated. It's not just this copying thing. It's a 16 by 16 transition matrix that we came up with in a very specific way, for which classifying better than random is NC1 complete. Very good? Okay. So what's the conclusion from that? So unless TC0 is equal to NC1, you need log n depth. But if TC0 is not equal to NC1, so this is a question that we don't know how to answer, then you need log n depth. Questions? Okay, so this is what we know about depths on this model. What's the depth score that you give? I don't know, I'll give a compliment to myself, maybe we'll give it a 7. Okay, it's just logarithmic depths, there's this conditional thing about TC0 and NC1, but it's it's somewhere going in the right direction. Very good? Questions? Okay, so now we have to decide what. I have another 30 minutes, okay, something like that. Okay, so 2 options, I'll let you vote. Who wants to, so the 2 options is to talk about sort of more realistic models. And, okay, maybe, okay, let me do this one slide and then I'll let you vote. You'll vote in a second, don't fall asleep right now. Okay, so this threshold is important. This threshold 2 theta squared is equal to 1 is called the Keston-Stigum theorem, and I want to tell you this threshold, and I want to tell you a little bit about this threshold because it also would answer a question that Seb asked about a while ago. So let me go through this, and a lot is known about this. So when theta is bigger than 1 over square root of 2, it's already known, not in this language, but it's known, that 1 neuron can classify the root better than random. This is a theorem of Keston-Stigum from 1966. So you don't need a deep net, you don't need even 2 layers. You just need 1 neuron applied to all the data. This 1 neuron is going to classify better than random. That's better than random, not as well as BP. So there's better than random and as well as BP. This is just better than random. Below this threshold, when theta is less than 1 over square root of 2, we know that 1 neuron cannot classify better than random. Okay? Yeah?
Does neuron mean single majority gate?
Single majority gate in the case of binary. In other cases, you have to do something else. Right? You have to take subspectral information about the Markov chain into account. But in the simpler case where there's just binary alphabet, it is just going to be single majority. But it's more general. And also below this threshold, with enough IID noise of the leaves, BP becomes trivial. So there's something interesting happening at this threshold. And it's also related to replica symmetry breaking in statistical physics. So this is a huge body of literature, which I'm just mentioning the connection there. The connection was made by Mézard and Montanari. But our conjecture coming from this, given this connection, is that for any broadcast process on the tree, below the KS bound, when theta is less than 1 over square root 2, and where BP classifies better than random, so for many broadcast processes, there is a range of parameters when this happens, classification is NC1 complete. Okay, so let me try to, maybe I'll draw a picture. There's a lot of information here, so let me draw the picture. So here's the theta axis. Here's 1 over square root of 2. And here's what happens here. So above 1 over square root of 2,
So here, and let's write this as the performance. So let's look at some more colors. I didn't think about this before. I should have made this before. This and this. And I'm now looking at the general model, not necessarily with alphabet of size 2. Okay, so here is a single neuron. Here's going to be single neuron. Single majority or neuron. So the performance is going to be up to 1 over square root 2 is going to be trivial, and above 1 over square root 2 is going to be somewhat non-trivial. It's going to look like that. Here's BP. So for generic models, there's going to be some critical point below 1 over square root of 2 when it starts doing better than random. And it generally will stay strictly above the single neuron behavior. Okay, so performance means like 1 minus the classification error, or how much better you do better than random. Okay, so this is if you want, what is the performance? Is the expected value of your predictor times the label, if these are plus minus 1. Okay, so it's the probability that they agree. The g of x is equal to that. Okay, so that's the picture. And our conjecture is that for any broadcast process, above this case, below this case bound, so in this interval over here, you need NC1 in order to do inference better than random. Okay? This is an interval where BP does better than random, single neuron does nothing. Now conjecture is that actually you need the full power of NC1 in order to do inference. You good? Okay. Now let's take a toll of what you want to do. Who wants to escape the room and have coffee? Okay, good. You're polite people. Who wants to see some proofs or proof IDs? Okay. Who wants more realistic model? They are not very realistic. Okay. So I won't have time to do everything. So let me try to prioritize. Okay, so I'll give one proof. Who wants to see AC0? That's the simplest one. Okay, who wants to see TC0? That's the second simplest one. Okay, who wants to see NC1? I won't really be able to show you that. Okay, yeah, okay. So I'll skip the AC0. So I'll say in one word for Seb, I'll say, have you ever seen the switching lemma?
Yes.
Okay, so you want to do something like the switching lemma. So you want to do something like random restriction. And what's nice is the broadcast process, this is just for Seb, the broadcast process has built-in random restrictions. What are the random restrictions that are built in? This process that we're talking about, with some probability you just fix the value to be 0, some probability you fix to be 1, and everything that you haven't fixed to 0 or 1 is going to take the same value recursively. So there is a random restriction built in, and then if you know the switching lemma, you prove some other switching lemma given this built-in random restriction. Okay, so that's what happens in this proof. For those of you who know the switching lemma, that's what's going on. Okay. So here's what's happening for TC0. So I'll tell you, so this is an interesting story that relates to the statistical physics. So I'll just tell you what's the construction of the circuit. So again, we are exactly at this case, Q is equal to 2. Our matrix is that, and theta is very close to 1. Less than 1, but close to 1. So the circuit is going to be the following. It is going to be, so we have, these are trees, so these are some huge subtrees. Here there are some levels. I am going to do a majority of this subtree. I am going to do a majority of this subtree, and of this subtree, and on this subtree. And then there's going to be a constant number of layers. In constant number of layers, I can apply any function I want. So I'm going to apply BP on these layers. Okay, so I'm using the fact that I have majorities, but I'm not using it directly, because I do know that majority doesn't classify as well as BP. Majority loses with respect to BP. So if I apply majority globally, it's not going to do well enough. Instead, I do majority on some subtrees, and then I apply BP on that. Okay, so what do you need in order to do that? The technical ingredient is an ingredient that we use in some actually work on block models, is that BP with noise classifies as BP without noise if theta is close enough to 1.
So
So what's the key here? The majority value here is a noisy version of the actual bit that was here. The majority value here is a noisy version of the actual bit that was here. So now I'm doing BP instead of the true values on noisy values. And the question is, what happens when you do BP on noisy value? Do you get the same performance or worse performance? It turns out that you get the same performance. This is a 50-page paper. You can prove only if theta is close enough to 1. It's not an easy proof, but you can use it. Okay, so that's something. Okay, for NC1, you have to use the word problem. You have to do worst case to average case reduction. Then you have to transfer it to BP. There's some real computational complexity work here, right? So it's not something I can summarize. Okay, good. And the broadcasters in this case actually has a second eigenvalue 0. Okay, so now I want to try to tell you how I actually started thinking about this problem. So I started thinking about this problem in a more complicated model that my friends and colleagues from MIT suffered hearing through multiple times. Maybe now they'll appreciate it more. This is a more complicated model which tries to be more realistic. And in particular, this model has the property where this Kesten-Stigum bound, this 2 theta squared equal to 1, plays a key role. So you'll see what it is. Okay. For this, I have to tell you for 5 minutes about phylogenetic reconstruction. Phylogenetic reconstruction is exactly this problem. You want to reconstruct the tree T. Our tree is this binary, and the data is going to be the sequence of colors at the leaf, right? So you have this. So the model here is just in phylogenetic reconstruction. Maybe I'll just draw it. Just draw another cartoon of a tree again. So we have the tree, which is unknown. This is a question mark. I don't know what the tree is. And then we get sequences of colors. So we generate one sequence of colors. We generate another sequence of color independently. And the goal from this, okay, so if you want to think about it in terms of information theory, there's the tree. You generate a bunch of sequences. And then the goal is to recover back the tree. So the unknown is the topology of the tree T, and you want to recover the tree T. That's what you want. Okay, so that's what Darwin does. That's what people in computational biology do these days. And what I'm going to talk about now is a semi-supervised learning setting where this is more like, this is how I thought about this connection to begin with, and this is the setup. So the setup, I'm drawing images, but I'm really thinking about it as DNA sequences. Okay, so you really think about it as DNA sequences. So this is the tree that generated the DNA sequences. And here, everything below this point is going to be a dog. Everything below this point is going to be a cat. Okay, I have some biologists in the field, and the biologists in the field label some of the objects that I found. They actually found this cat. They gathered DNA sequence. They said, this is a cat, this is a cat. Then I have some other DNA sequences, which I don't know if they're cat or not, because I don't know where they lie on the tree. Okay, if I have a dog, I have question mark, I don't know where they lie on the tree. So that's the semi-supervised learning setting. And what I proved when I started thinking about this model is suppose that 2 theta squared is greater than 1, we are above the Kesten-Stigum threshold, then for any number of colors, under some parameters on this model, which I can list in a little bit, there is an algorithm that labels all the data correctly. Okay, so again, what's the semi-supervised setting? You are given the DNA sequences of everybody, and for a small sample of the guys, you actually get their labels. Okay, so the labels tell you if it's a dog or a cat, and there is an algorithm that labels all of them correctly. Right, and the second theorem is an important feature. Okay, sorry, so. Okay, sorry. So this is the most important slide. So let me just write this slide over here. So there are two theorems here, and there's some contradiction between them. And it's related to the power of algorithms. So theorem 1 says, if 2 theta is greater than 1, so theta is greater than 1/2, and Q is large enough, you can label all data correctly.
The second theorem says, if 2 theta squared is less than 1, so theta is less than 1 over square root of 2, any shallow algorithm, and I'll have to explain what I mean by shallow, cannot label better than random. Okay, so again, there is a range of the parameters where this parameter theta is between 1/2 and 1 over square root of 2, where there is an algorithm that labels all the data correctly, but this algorithm cannot be shallow. So I'll have to define what shallow is, but there's a separation here. You need some definition of depth in order to solve this semi-supervised learning problem. So let me try to explain what shallow is. So shallow is not going to be in a formal sense as we had at the first part of the talk. The definition of shallow is a little annoying, but I'll give you anyway. What is a shallow algorithm? So a shallow algorithm cannot use higher order statistics in the labeled data. Definition. I'll write the informal one. Shallow algorithm cannot use interaction between features in labeled data. So what does it mean formally? So the input to the shallow algorithm is the following. There's a set of labeled, unlabeled data, and there's the set of labeled data. So from the unlabeled data, you get all of the information. You get everything that you want. You get the DNA sequence of all of the labeled data, unlabeled data. For the labeled data, I'm just telling you, you want to know something about dogs? Here's what I'm going to tell you about dogs. So one option is, so if you want labeled dogs, which is not what I'm giving you, is to tell you, here is dog number 1, here's the DNA sequence of dog number 1. Here is dog number 2, here's the DNA sequence of dog number 2. All the dogs that I labeled, I'm going to give you the DNA sequence. In unlabeled data, in the shallow algorithm, the only information that I'm giving you is summary statistics. I'm telling you, what's the distribution of this column? What's the distribution of this column? What's the distribution of this column, and what's the distribution of this column? I'm giving you the empirical distribution of every column, maybe even every pair of columns, every triple of columns, but up to order, log, and statistics. Okay? So what's the key idea here? The key idea is that one of the things that people say about DeepNet is one of the things that they need to do is they have to use interaction between different features. What I'm saying here is like, let's not give the reconstruction algorithm any information about the interaction between features. How am I going to do it? Just for the labeled data, I'm going to screen the information. How am I going to screen the information? I'm not going to give you the actual representation of each object. I'm just going to give you summary statistics of all the objects that are dogs and all the objects that are cats. We're good? Okay, so that's somehow what started this work. Some people are still following. Okay, good. So that's somehow what started this work. And then, when I started this work, the question is, can we do this for more complex models? What I did in these more complex models, okay, so this is the phylogenetic model. You have these DNA sequences, and you have this mutation. And one of the things that I could do pretty easily is I added another level of interaction where instead where you go from one level to the next, you just have these random mutations. You also have discrete convolutions between the guys. Okay, so I take, in the DNA model, each letter evolves independently. Now I said, oh, adjacent guys are going to convolve together, and then guys at distance 4 are going to convolve together, and then guys at distance I are going to convolve together. So I'm going to do some notion of discrete convolutions like we do in convolutional nets in order to get from the top to the bottom in order to mix all the features. And the key fact is that you can prove the same thing for this kind of model. Is this realistic? It's not realistic. I don't know any data that it represents, but it looks a little bit like running deep nets forward. We're good? Okay, so maybe I'll stop early and I'll mention some natural challenges. Some more realistic models and testing on data. One thing that I like, I mentioned this question to Shai Shalev Schwartz 3 or 4 years ago, and with a student, Malach, they looked at image models that have these features, and in these image models that have the features, they claim that these models are realistic. Definitely, there are more realistic models of images than anything I thought about. And they have provable reconstruction algorithms for their models, which is nice. They have no depth lower bound, but at least these two features they cover. And this is a little snippet from one of their papers. So these models, which similarly to what we talked about, and similar to Malat model, you go from this top down. You apply some simple probabilistic recursion of how this patch is becoming this patch, is becoming this patch, and so on and so forth. And they have provable algorithm of recovering data of this sort. Again, they don't have proofs of depth, but this is something in the right direction. Good. So I'll stop here. I think there are many interesting questions here. Let me just mention what they are. I think the most interesting question maybe is to try to interpolate between the sort of theoretical aspects here and more realistic model. I think, even in the Shai-Shalev-Schwartz setup, there's questions about proving lower bounds. I think even maybe more exciting is to try to bridge between the models that I presented and something like the scattering transform. I think I think somehow if one can interpolate between these two models and build a good theory that encompasses both, I think we can actually get something pretty interesting. So I'll stop here. Thank you.
We have lots of time for questions.
And question. Yeah.
You mentioned that there is convolution between the species, like if it's dogs and the cats. But can there be interaction between the two of them?
No, in this model there isn't. So a very good question, which again, I think this is completely open. I think, in this particular graphical model, I'm the only person that's doing it. But even if you look at models like Malat models, there are sort of three models. And they don't think so much about interaction going in this direction, right? So I think that's another level of complexity that one can add and can add something, but so far it hasn't been explored.
Yes, because I was looking not from the images, but if you have complex systems which are there, and if you have to detect some interaction between those systems,
Yeah, might be interesting. Yeah.
So I thought wavelets would already give you multi-scale, multi-resolution analysis. So maybe
in what sense? In what sense?
I mean, you can look at images of different scales, different resolution, and it gives you this, coefficients at different scales, which would
like in Fourier analysis. I mean, you already have high amplitudes and low amplitudes. I think that's not the issue. That's not the thing with the scattering transform, right? So you're asking what additionally we get? Do we get
scattering transform?
Right. So I think the additional feature that we get. So you want a so what they really want is they wanted a generative model for images. Okay. So the generative model will just give you a wavelet expansion, but you want this generative model to have this feature that it's continuous with respect to deformation. And the question is, how do you do it? You said, okay, if I apply some low filter at a low level, I know what it does. It kills the high levels, whatever. But if you do higher level things, right, you would shift it globally, you contract this part more and this part less, it's less clear what would you do in the wavelet world. And that's the reason that they came up with this model. The other nice feature of this model is, again, if you look at somehow when you go back in this model, all the information that you have is low amplitude. You have no high amplitude information. Somehow when you do this, the inverse operation of the scattering transform, you get this high frequency information. I hope it helps. Other questions?
Okay, so we'll come back at 11:10.